Hello students, let's continue with our study of energy. The mechanical energy of a system is going to be the kinetic energy of whatever it is that's moving, plus the potential energy of the parts of your system. We're not including thermal energy here. So we're not taking into consideration what the book calls non-conservative forces, like friction forces. Instead, we're only focusing on the energies that have to do with the conservative forces. Okay, the mechanical energy has in it the kinetic energy, and the formula for kinetic energy is 1/2 mv squared. And it has in it gravitational potential energy. And to compute the gravitational potential energy, it's the mass of whatever it is times g times the height. And the height is going to be relative to some reference location. Now, sometimes you might want to have like a different height, a different reference location. Like maybe you want to be measuring from this place, and so now your height might be this height. And that's okay. You just need to decide and then not change your reference location. You just need to be consistent. Whether you pick this height or some other height won't make any difference. It'll cancel out in the end. Okay, and then finally, let's continue. We have that if you have springs in your system, then your potential energy, or the part of the potential energy having to do with springs, is given by 1/2 kx squared, where x is the displacement of your spring. So if you have the spring squeezed to this place, then so x is this distance here. And notice that since it's 1/2 kx squared, this thing ends up being a parabola, and right, it's a quadratic, so it's a parabola. So over here, you're compressing the spring, positive x, and you could be stretching the spring, and then that would be the negative x case. Okay, so we have an object which can be high or low, it can be moving, and it could be bumping up against a spring. The law of conservation of mechanical energy says that if your system is isolated, there are no forces coming in from the outside, and that there is no friction, then the total energy E is going to be constant. So this has various implications, but the most important implication is that if your kinetic energy, you have, let's say, kinetic energy here, potential energy here. If the kinetic energy goes up, then the potential energy has to go down in order for the sum of the two to be constant. And if the potential energy goes up, then the kinetic energy has to go down. So you're going to have this back and forth. All right. Okay, so this is one of the Pivot Interactive Labs, and you have a dry ice puck, and when I do this, you're going to be doing this. You see the dry ice puck slide down the hill. It's virtually no friction. There is a tiny bit of friction. That's something you figure out in the lab. And so this is a really nice demonstration of conservation of energy. So let's reset this thing, and I want to show you the kinds of potential energy that we have. So the first one is gravitational potential energy. And we can figure out the gravitational potential energy by just measuring how high the puck is. So we're going to need a reference line. We're going to need to decide where the reference, we could put the reference line here, but I'm going to put it down here. And you guys will get it just right. I'm not going to do it perfectly. So when you do the lab, you're going to know the height relative to your reference line, so relative to 0. And so the potential energy, gravitational potential energy, is the height of this thing. So now, when it goes, let's let it go down. Now, that went a little too far. Let's back it up. When it's here, the kinetic energy, which was originally 0, 1/2 mv squared, v was 0, but now it's down here, it's moving, so it's got kinetic energy. So the kinetic energy has gone up, but it's gone down, right? Its height is less, so its potential energy has gone down. And one way of thinking about what's going on here is you could say, wow, gravitational energy is being transferred into kinetic energy. And transfer of energy like this, that entails work. And so what's going on is the gravitational force is doing work, and that work is moving gravitational potential energy into kinetic energy. Now, this continues until we get to, let's see, one more. Oops. It's already rebounding here. Let's go and do this. Okay, well, here, since it's here, now you've got the spring has been squeezed, and so 1/2 kx squared. The spring's potential energy has gone up, but what about the other energies? Well, the gravitational potential energy has gone down. The kinetic energy has gone down, right? It's stopped. So the spring now has all of this energy, and the kinetic energy has gone down to 0, and the gravitational potential energy has gone down to 0. So we have like 3 different pots of energy which are going up and down, but if you look at the sum total of the 3 different kinds of energy, the total energy stays constant. And when you do the lab, you're going to get to see that. I hope the lab works well for you.